So next two sectors we'll look at under AI for mitigation. Climate mitigation is materials innovation and reducing emissions from the food system. As we know, agriculture can emit up to 30% of total emissions across the globe, and so on. So we'll come back to that. This is just some examples. Roman concrete enabled extraordinary construction projects, including the Pantheon, the world's oldest building still in active use, I think in Paris, if I don't make a mistake there. Materials innovation enabled the development of lithium-ion batteries for electric vehicles, long duration grid storage and other low-carbon technologies. The discovery of the vulcanization process transformed natural rubber into a highly durable, extremely useful material. Solar photovoltaic systems are the product of years of material innovation and optimization. So AI has played a role in all these things in some way, even though we didn't always call it AI in olden days. It was just statistical approaches. So what are the innovations in material synthesis? In some cases, the limitation to the performance, obviously Romans didn't use AI, but they did some research that gave them a concrete that could last forever. So we have to be careful. In some cases, the limitation to the performance of a technology could be overcome by a well-known material that has superior properties, but a practical method to produce this material is not known. So the Roman concrete could be one of them. One such case is the general illumination LED bulb, now in common use. Although LEDs were originally invented in the 1960s, they were based on a material gallium arsenide, or GaAs, that can only emit red light. Researchers knew that gallium nitride and zinc selenide could enable white LEDs that could be used for general applications like building and street lighting. However, it was not until the development of the two-flow MOCVD, metal organic chemical vapor deposition reactor, in the 1990s that gallium nitride crystals could be reliably produced. So doing it in the lab is one thing, but then you need manufacturing technology readiness levels. This development led directly to commercial white-colored LED lights with dramatically higher energy efficiency than incandescent and fluorescent bulbs, which are now gradually being replaced. Notably, although LEDs have reduced the energy intensity of lighting significantly, global CO2 emissions from lighting have not fallen because the demand for more lighting has offset these efficiency gains. This is called a Jevons paradox, where something gives you more efficiency, which means people will just start using it more, or you can also call it a moral hazard. So here are some more examples. Yttrium barium copper oxide, YbCO, was one of the first high temperature superconductors to be discovered by AI, I suppose. So these are the companies and organizations involved here. So that's the nice structure up there. So innovative materials are important for enabling carbon capture and removal systems, such as this direct air capture plant in Iceland. So it has a flow-through system and precipitates out carbon dioxide. There are also metal organic frameworks that do adsorption and the desorption and so on. Finally, just jumping ahead, advances in accelerating materials discovery and design with AI depend on improving the AI knowledge and skills of the materials science workforce. Key issues in AI, such as understanding the applicability of trained AI models to problems outside the domain of their training data and quantifying the uncertainty of model predictions, are challenging and likely unfamiliar to conventionally trained materials scientists. AI tools should therefore be incorporated as a central part of the materials science education, and training should also be offered to AI experts who are interested in applying their skills to novel materials development. These education and training efforts could take place within traditional materials science curricula or as a part of external courses that can ensure the most recent models, numerical algorithms, and data sets are presented and continually updated. So kind of upskilling workshops or short courses that can take the latest innovations in AI applications for materials innovation. Okay, so summary. Advanced materials with special properties are essential for decarbonizing many parts of the economy. Products including catalysts, battery anodes, solar photovoltaics, wind turbine blades, refrigerants, superconductors, carbon capture sorbents, and high-strength magnets depend on advanced materials. Historically, advanced materials have been discovered through accident or tedious, expensive trial and error. Advances in computing power and materials science theory enable the transition to a more computational basis for materials discovery several decades ago. However, the methods for identifying potentially valuable novel materials through computation require large computing resources and are still too slow to fully meet the needs of materials innovation for a decarbonized economy. So it's often about mixing, making concoctions that work, and there can be infinite combinations, but AI can help there. Computational materials science has begun using AI methods, and they are already having an important impact. In some cases, AI models can replace fully science-based computations, greatly speeding up processing times. AI can also help interpret results of material characterization experiments, enabling rapid, high-throughput testing of advanced materials candidates. Natural language AI can scour the vast materials science technical literature, summarizing thousands of published research articles to enable rapid, accurate literature reviews and surface harmonized process steps for materials production. Most recently, generative AI methods have begun to suggest entirely novel classes of advanced materials that had not previously been envisioned as relevant to emission reduction applications. While these advances are highly promising, much better integration between material science and AI research is still needed to realize the full potential for climate mitigation in terms of AI application for materials innovation. Now we will move into what is this food systems. Okay, so here is smart agriculture. A guy with the iPad or some device is tracking lots of different data to monitor yields, stress, pest infestation, and so on. Here is mechanization of agriculture. Here is some organized farming, and here is some lab work for, you have genetically modified organisms, is it, for, improving yields, drought resilience, pest resilience, and so on and so forth. So it is about land use change and food production. So what can AI do? Help map renewable energy solutions, classify land. This is the easiest way to apply AI without doing much additional work, but of course you need data. Balance solar resources for food and energy production. Observe and predict deforestation event. Soil carbon sequestration to reduce emissions and mitigate climate change. So soil is an important sink of carbon, but agriculture tends to mostly make it a short cycle of uptake and emission. So AI can be used to optimize the soil carbon sequestration for longer times by managing agriculture, irrigation, fertilizer use, and so on. Okay, so in food production you can enhance productivity. So precision agriculture employing AI can increase efficiency and conservation gains without sacrificing yield outcomes. Examples include watering and feed management, controlled crop management, automation, and advanced livestock and crop health monitoring, including identifying field stresses and impacts from pests and pathogens through image processing and neural networks. In addition, AI can help decrease food loss during harvest, maximize the potential of using bioenergy and biomass for greener farming inputs such as fertilizer. Okay. Finally, derive new and enhanced models of farming systems. Well, not finally, we have a few more. Forecast crop yields and loss. This is already happening, especially for reinsurance companies, because a lot of farmers buy crop insurance and then something happens and crop yields increase or decrease, and reinsurance, insurance companies have to pay it out. Develop alternative proteins. AI methods can be leveraged to improve innovation around plant-based and cultivated meat, which can lead to consumption of food with smaller environmental footprints. Lab-grown meat, plant-based meat, etc. are now becoming more and more common. Supply chains, optimize food supply chains, obvious target. Improve food packaging. Through simulations and predictive analytics, AI can assist in improving the design, materials, and energy usage for packaging food items. Consumption and waste. Forecast consumption patterns, streamline disposal process, and sort waste. And countries like South Korea have gone to great extent to reduce food waste and compost them and so on. Of course, there are financial considerations, cost-benefit analysis needed as well, because no matter how good it is for the environment, unless it can be sustained economically, it's going to be difficult to sustain, right? Key considerations in using AI to mitigate food system emissions then: develop protocols for stakeholder-driven AI applications and tools across food systems. Increase transparency, accountability, and standardization in AI decision-making and data collection in food systems. Expand and scale existing technologies to effectively mitigate food system emissions. Invest in AI research and innovation explicitly tailored to food systems. Promote collaboration and public-private partnerships to facilitate scalable emissions reductions strategies across land use, production, distribution, consumption, and waste. Obviously, we'll need collaborations between public, private, academic institutions, researchers, and so on. Ensure inclusivity and accessibility. This is always critical for all applications of AI, which we talked about in one of the previous podcasts. So the summary of this chapter then: food systems including food production, processing, distribution, consumption, and disposal are critical to health and livelihoods worldwide. Food systems are responsible for more than 30% of global GHG emissions. Climate change, in turn, has a significant impact on food systems themselves. AI has significant potential to help reduce GHG emissions in food systems, including by integrating data from multiple sources such as soil sensors and satellites to recommend fertilizer application schedules, irrigation application schedules that mitigate nitrous oxide emissions while maximizing crop yields, water savings with irrigation without crop yield loss, and soil waterlogging, etc. also can be helped. Anticipating future needs for precision fertilizer applications under a range of projected climate conditions, analyzing data on biomass characteristics, growth rates, and carbon sequestration potential to optimize feedstocks for biomass carbon removal and storage, increasing renewable energy generation by optimizing land use for multiple purposes, forecasting pest and disease pressures, of course, developing alternative protein products which have a much lower carbon footprint than animal-sourced foods, and reducing loss and waste through intelligent harvest timing to prevent food spoilage. Food waste produces about frog in my throat produces about 6% of the total emissions, and even poor countries waste a lot of food. So reducing food loss and waste is a very critical component of reducing emissions from food systems. So AI provides a set of complementary tools for reducing food system emissions, not a solution itself. Proper use of AI technologies should be grounded in scientific knowledge, physical constraints, well-defined public policy objectives, ethical considerations, and a nuanced understanding of the complex operations of food system stakeholders. We'll come back and look at EVs, so transportation, this is what this is, and then next one will be just overall recapping the barriers of applying AI to climate mitigation. Okay, this one is already over about 15 minutes long. That's okay, we'll leave it and come back to the next sector and look at some barriers overall in the application of AI for climate mitigation. See you.